Hey, we have finally reached chapter 5. We're looking at polynomials. Section 5.1 will be about monomials. We have a large number of vocabulary words to talk about, but before we even do that, we need to talk about exponential laws. Hopefully this is a review. If not, make sure and take some notes. So exponential laws. First of all, what is an exponent? You've seen things like this, 3 to the second power. Hopefully you remember that the answer to something like this, 3 to the second power, is equivalent to 9. What that means is take two threes and you multiply them together. Suppose you had like 2 to the fourth power. Hopefully you know that they means to multiply 4 2's together for the grand total of 16. So 2 to the fourth power is 16. The number here we refer to as an exponent or a power. The number that's being raised to a particular power is called the base. So in this particular expression, 2 to the fourth power, 4 is the exponent, and the base, I'm sure you guessed it, is 2. All right, so with that bit of information, let's talk about some laws. All right, so the first law refers to multiplying two numbers with the same base and perhaps different exponents. So I have x to the m power times x to the n power. What would I get? To think about this, I will start off by taking 3 to the second power, multiplying it by 3 to the third power. What this really means is that I have 2 3's being multiplied here and 3 3's being multiplied here. Altogether, grand total of 5 3's. So that would then be 3 to the fifth power. The question is, what did I do with 2 and 3 to get the 5? Hopefully you see that I added it. So coming back to this general rule, if I have x to the m times x to the n, it would lead me to get x to the m plus n. That's rule number 1. Our second rule refers to division. If I have x to the m over x to the n, or I'm dividing the two, what would happen? Again, an example is a good idea here. If I have 3 to the fifth power over, let's say, 3 to the second, I recognize that the numerator, the top part of my fraction, has 5 3's that are being multiplied together, and the denominator has 2 3's. And you've seen this before. Basically, the opposite of multiplication is division, so I can divide the top and bottom by 3 each time. These guys cancel and give me 1. So now I end up having 3 times 3 times 3, or 3 to the third power. So the question stands, how could I have gotten this exponent of 3 from the numbers 5 and 2? Hopefully you see that 5 minus 2 is 3. And we get that the rule should be x to the m divided by x to the n is x to the m minus n. All right, so let's take a look at the next rule. So we've got x to the m raised to the n power. And what this is really is something like if I had like 3 to the second power raised to the third power, that would mean I'd have 3 of these things. So that would be like 3 to the second times 3 to the second times 3 to the second. From this first rule, we know when we have the same base with a bunch of exponents or different exponents or even the same, we add those exponents up. So this is really 3 to the 1, 2, 3, 4, 5, 6 power. What can I do with 2 and 3 to get 6? You guessed it, multiply. So when I have a power to a power, I multiply my exponents. So this is x to the m times n power. Our next rule refers to when we have a product of two numbers, let's say x times y, and I'm raising that entire product to the m power. What that tells me is that everything in the parentheses will be raised to the m power. So I could rewrite this as x to the m times y to the m. Rule number 5 is the quotient of two numbers raised to a power, and similar to rule number 4, it'll end up being x to the m over y to the m. Notice that the exponent is, in a sense, distributed to everything inside the parentheses that is being multiplied together. One caveat, if I had like x plus y to the m power, it does not equal x to the m plus y to the m. This is a whole nother category of stuff to deal with. So this is something that I want you to pay attention to, because a lot of students, even like my upper level math students, they always make this mistake. So don't do that. So the only time we can raise everything in the parentheses to the m power or whatever power is on the outside is if all of that stuff inside is being multiplied together or divided together. If we have a situation where it's being added or subtracted, it's going to require us to do something different. So this rule only refers to this situation. We've got 2 more rules to go. Let's check them out. So these last two rules are the type of thing that students accept but don't always understand. So the first one is x to the 0 power is equal to 1 all the time, forever and a day. And I'm going to explain this by telling you or asking you, what is it if I put 100 over 100? What does that equal? Hopefully you said 1 and you'd be correct. If I put like 5 over 5, still 1. If I put 3 to the 5th power over 3 to the 5th power, whether you knew what 3 to the 5th power was, the fact that it's the same thing over the same thing, you know it's equal to 1. Well, let's stop here for a second and think about what this means. If I have 3 to the 5th power over 3 to the 5th power, back up here in rule number 2, we know that when we are dividing numbers with the same base, we can subtract their exponents. So what would happen if I subtract this thing that I already know is equal to 1, if I subtracted the exponents? I would get 3 to the 5 minus 5. 3 to the 5 minus 5 is also written as 3 to the 0, which we already know to be 1. We can do this with any number, and so we can carefully and comfortably conclude that x to the 0 power is equal to 1. And I don't need any more equal signs because that's all we need to know. Let's look at the last and final rule. All right, so we have x to the negative m power. When we raise something to a negative power, I need to just tell you this straight out. You will never make a number negative by giving it a negative exponent. That's not how you make another number negative. So that's not what this is going to do. We need to think about this. Well, first I'm going to give you the answer and I'm going to explain why. The answer is x to the negative m power is equal to 1 over x to the m. Notice that we have the same power, but it's no longer negative. It's dropped into the denominator, and we've got a 1 on top. Let's talk about why. So if I have 3 to the 2nd power over 3 to the 5th power, you know that I could write this out as 3 times 3 at the top, 5 3s at the bottom, do a little bit of cancellation, boom, 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 boom. These cancel out to 1s, so I'm left with 1 over 3 to the 3rd power, okay? We also know that we could have looked at this problem in terms of rule number 2, which tells me to subtract my exponents. So what happens when I subtract 2 minus 5? If I have 3 to the 2 minus 5, I really have 3 to the negative 3rd power, which I know now is simply 1 over 3 to the 3rd, because we got the 3 to the 2nd power over 3 to the 5th power. We said it was equal to this from rule number 2, and therefore it's equal to this. But we also calculated that 3 to the 2nd over 3 to the 5th power is equal to 1 over 3 to the 3rd. So these guys must be equal too. And so that's an illustration of why this is true. So if you ever have, let's say, x to the negative 3rd power, you'd rewrite it as 1 over x to the 3. If you had m to the negative 2nd power, you'd rewrite it as 1 over m squared. Get the picture? All right, so those are the laws. If you don't know these, you need to memorize them. They need to be kind of second nature in order for you to answer any of the questions that we're going to work on in this section. Let's talk a little bit about some of these vocabulary words. So our first vocabulary word is monomial, and a monomial, as it's stated is here, is an expression that is a number, a variable, or a product. Product means we're multiplying of a number and one or more variables. So here's a few examples of monomials. These guys aren't monomials, and I'll tell you why. Because first of all, monomials need to have a positive exponent. As you notice, all of these do. This one does not, so this is clearly not a monomial. Monomials also are only multiplying variables together, so all of these variables are being multiplied together. Here b is multiplied with 5, w is technically multiplied with a negative 1, 23 is a standalone number, which is cool, x times x being multiplied. All of this is being x to the 3rd power, all being multiplied. Here we have this one being divided by n to the 4th power, and so therefore it's not a monomial. Also, the powers of our monomials need to be whole numbers, and so whole positive numbers. And you don't know this now, but this radical indicates that you don't have a whole number power, and we'll talk about that probably our next lesson or so. And x plus 8 is not a monomial because notice that there's nothing being multiplied there. Literally, we have things that are being added together. So monomials look like this. They could be a whole bunch of different array types of things, but one thing you want to know is that it's going to be a whole bunch of stuff multiplied together. So that's a monomial. Our next word is constant, and constant is just what it sounds like. It is something that never changes. It is constant. And if you have a number by itself, 2, 4, negative 1,000, negative 5 over 3. These are all considered constants. They're standalone numbers that are hanging out by themselves, and they are just going to be what they are. They're constant because they don't change. A coefficient is a number that is next to a variable, a monomial that has variables. So if I have 2x squared y, and that's my monomial I'm talking about, the coefficient of that monomial is 2. So it's the number that is being multiplied next to the rest of the monomial. So 1/2 x squared. In this case, 1/2 is the coefficient. The degree of a monomial refers to the sum of the number of variables. So for instance, this is a monomial. Negative 3, let's make that a negative 3 x squared y to the third power. Let's even throw a z in there. How many variables are here? Be careful. The number of variables, the fact is this is not just one x, it's two x's. So there's two x's here, 3 y's, 2 plus 3 is 5, and 1 z. The degree of this monomial would be 6. Or I should say 6th degree. It's a 6th degree monomial because it has 1, 2, 3, 4, 5, 6 variables. Yes, I'm counting x squared twice, right? The degree of this monomial that I'm going to put down here, let's say negative 2/3 x, is just 1. This is a 1st degree monomial. So the degree is just the number of variables that are being multiplied together. And we did talk about power. Before, power is often used interchangeably with the word exponent, and we're going to talk about simplify. To simplify means to rewrite an exponential expression with no negative exponents, none whatsoever. And we'll be doing that shortly. And I'm going to stop there. We'll get to these other topics in a second, but I just want to get through some example problems. So let's start with example 1. So we're going to simplify this expression with multiplication. So we're going to join all this stuff together. We got a whole lot going on. We're going to join it together and simplify by multiplication. So we'll start off by multiplying what we can. So all of this multiplied with all of this basically means that I have all of this stuff being multiplied together. So what I'd like to do is I like to think of it as multiplying what I can first. I can multiply 3 times negative 4 pretty easily. I get a negative 12. Now I'm going to bring the x's together. Here I have x to the third power, and here I have x to the second. Well, when I bring those guys together, if I've got 3 x's here and 2 x's here, altogether I have 5 x's, right? This is rule number 1. When I'm multiplying the same base, I add the exponents. Similarly, I'm going to apply rule number 1 here. Multiplying 2 numbers with the same base, add the exponents. I've got y to the 6th power. And this, my friends, is how I simplify. So I've simplified this expression pretty neatly. It's nice and compact. There are no negative exponents, and I'm good to go. Here in example 2, we're going to simplify an expression that is division. Remember, when we simplify, we ultimately do not want to have a negative exponent. So let's see what happens here. This looks like a great candidate for the rule number 2 because we're dividing. So p to the third power over p to the 8th is equal to p to the, that was a b, my bad, is equal to p to the 3 minus 8 power, which is then p to the negative 5th. Here's what I want to hold on to for a second. We would actually write this from rule number 7, 1 over p to the 5th, right? Because that keeps us from having a negative exponent. I want you to know that the reason why this is added to the problem is not to confuse you. It's to say, hey guys, we're being legal. If p were equal to 0, we couldn't divide by it. So we're saying p is not equal to 0 in this expression. This does not require you to do any work. This is really just a person who's asking you a question to say, hey, what I'm doing is legal. So don't sweat that. But the answer to this problem is 1 over p to the 5th. Nicely simplified and no negative exponents. In example 3, we're simplifying some more, but in this case, what we're going to do is we are going to use a couple of different rules. This is our power to power rule. Power to power tells me to multiply, so this would be a to the 18th power. This is like, I'm going to distribute this 5 amongst all of this stuff in here. So technically, this is what we have, and if I were to honor each of those, I'd get, and this would be my answer.